Okay, let's start. Good evening, everyone. Welcome back to CPE 460 Introduction to Edge AI Techniques 1. First of all, let's finish our lecture 8. So in the previous lecture, we mentioned the motivation of logistic regression, the models of logistic regression, and uh, in today's class, when we talk about multi-class, support vector machine, you will see the logistic regression model here applies an idea of all against one actually, and then we use multi-knowledge distribution to model for the label Y, and then after this we use MLE maximum likelihood estimation method to let me make it bigger. Sorry. Okay, to derive, the expression for the parameters estimation. Parameters are those beta J0 and the beta J vectors. And then we have to use let's say numerical method for example, this iterative reweighted least squares method to estimate to finalize the parameters. Okay, and then we introduced example one, which is a very simple example for logistic regression here. Training the model, make a prediction. Be careful that the test data set must be 2D and 1D, and then plot everything, decision origin, something blah blah blah. That's it. And yeah, we finished example 8.1, this example in the last class. Today let's introduce example 8.2. So logistic regression is commonly used in credit card approval denial system. And that's the reason, nowadays, if you try to approve, you just try to apply for a credit card, it takes typically, I don't know, 30 seconds, 1 minute, to give you the decision very, very quickly. You may not believe in 1980s, 1970s, all of these were done by human. You had to mail a letter, and then they will check, your application and manually make the decision, and then email the credit card. Sorry, no, there's no email. There was no email. Mail you back the decision, and if you were approved, then they will mail you back a credit card as well. Super slow, but nowadays, super fast. How could we make it? Here we go. LGR, logistic regression. So here, just open the data. So in this data set, we have I can actually do it here. In this data set, we consider one, two, three, four, five, six, seven features. The first column is approval or not. One means approved, zero means denied. And then these things are the age of the applicant. To make the applicant legal, the person must be 18 plus years old. 70, I'm not sure because I downloaded this data from somewhere else in which, the explanation of the age is 70. That's why I put 70 here. Married or not, uh, this is, I don't know, but, it's a very, very standard feature for no matter tax return or credit card application. In general, I believe that they believe that if a person is married, then the risk is gonna be lower because the person has to consider the spouse and also children. And the third thing is education level. So it's a well, here's the typo. Sorry, so sorry. I just realized here's the typo. I even didn't see it. 5, 4, 3. This should be two. High school, high school level or what should or lower should be two. High school should be two. Sorry, high school is two. Lower than high school is one. In general, we would say higher educational degree, lower chance to default. In general, okay, it's not absolute. Years employed, number of years being full-time employed. So typically, the more years you've been employed, the lower risky. And prior default, the number of defaults in last year. Income is the annual income last year, unit to 1,000. Credit score is the current credit score. Let's have an example. Let's check an example. Let's say here, this person, age is 33-year-old, married, yes, married, education fine, means PhD degree, 6 years of fully employed, prior default, which means that the default in the last year, 0 times good. Income is 92,000. Credit score is 805. Uh, by our common sense, let me remove everything join here, sorry. By our common sense, we can clearly see this is a very, very good candidate, and the candidate is approved. See another example here, age is 20, not married, education 2, I believe high school. Yeah, here should be 2 again. Here's a typo, 2 and 1, okay? 2 is high school. I years employed 0. So the applicant has never been full-time employed. Prior default also 0. Good. Income is 14,000. Credit scores are below 593, and the decision for this person is 0, denial. So, so we have totally how many training data? Let's say 68 training data. Okay, now I'm asking you, to build a LGR logistic regression model based on this 68 training data. And then we will test the data, which is this data. This data is 40, means the person is 40-year-old. 1 is the person's married. Education level 3 means undergrad, I believe. Yes, bachelor's degree. Years of employed is 16. 16 years of employed. This 0, I believe, default. Yeah, prior default is 0. The person has never default, in the previous year. And income is 50,000. Credit score is 600. And I want the model to make a prediction whether we should accept or denial on this person. So this is the thing. And you may not believe that this system is really, really, practical. In a real system, I don't know now. What I knew was one of my friends got, a job in the bank, Discover or which bank? I forgot. And exactly working in credit card system prior, before the pandemic. And he told me that the system, the way they are doing it is really, really, really similar. And the logistic regression is one of the most applied method in there. So I would say it's a pretty, pretty good, thing because it's super fast. You will see logistic regressions really, really fast. And okay, let's do this example together. So first of all, here I'm to import many things. Import ISMP, import pandas as PD. The reason I need to import pandas because I need to use CSV read here. Read the CSV, sorry. That's why I need this. Here I don't need a matplotlib because I'm not gonna plot anything. So I'm gonna need to have the logistic regression sklearn dot linear model import logistic regression. Okay. So first of all, I need to get the data. Data equal to PD dot read CSV. And what's the data? Is it? Sorry. This dot CSV. Okay, then I'm gonna x equal to data dot job. Let me see which one shall I job? Approval. Access equal to 1, meaning that I'm gonna drop a column instead of a row, and then y equal to template data approval. Okay, so now I have xy. I can build a model equal to logistic regression model dot fit xy, and now I can make a print. Let's say print the training accuracy. First of all, I want to know is model.score x and y, and then give it a digit, let's say 3f. Let me see how many did I use? 4F. Oh, I just realized here I also use a solver. Yes, this is something I want to mention. So this was a package returned by a professor in I forgot which university. But the point is this National Taiwan University. The point is that is a pretty strong, powerful solver. So this example we only have 60 how many 68 training data. Real example is supposed to have millions of training data. I would say million may be too many because this is powerful for those kind of small data sets. Let's say you have 100,000, 10,000, all these are very small data sets. This, solver, live linear is super fast and provide a very good accuracy. And hence, this is a very good solver if your data set, training data set is not too big. The problem is how big is big. My personal definition, I would say, let's say 100,000 is a pretty, let's say, like a small data set. If any data set is below 100,000, I will absolutely choose this one. Or I can just leave the blank. The default solver, I believe, is, let me see. Actually, I don't know. What is the default solver? Let me see. Solver. Default solver is BFGS. If you're not familiar with that, it's a BFGS is a super famous numerical method. Also use a gradient method, which is you move towards the gradient direction and move somewhere, and then judge whether it's convergent or not. But that's something about the numerical methods, computational methods. Too long to what expand it. Just to let you know, if the what data set is not small, is not big, you may want to consider this one. Okay, so let me apply it here. Let me close both of them. And then let me apply here solver equals to lib linear. If our is that lib linear? Let's see. I remember library. Yes, lib linear. Okay. And here's a 4F, not 3F. Okay, so like here, I can just print it to how come this one is wrong? Wait. Model.fit xy. Huh? Let me see. Wait, how come this is wrong? Let me just check. Wait, that means the solver labeling here is wrong. Wait, 1 minute. Oh, okay. Sorry, my fault. I don't know why. We're pretty dumb. Okay, here we go. So we can see that the training accuracy is pretty good, 92%. Okay, so now I want to generate a test data. Let's say generate a data, let's say an applicant for test. And the X test is 41, 3, 16, 0, 50, 600. Okay. 41, 3, 16. And then what? 0, 61, 0, 51, 600. Yes, 0, 50, 600. Okay, so now I have this. I want to ask, hey, how is the result? So model y predict equal to model dot predict X test. And then don't forget here, I need to make it an as type int, as type. Why? Remember in the previous example, if you don't use where this where this here, if you don't use as type int, it will show you class 1 dot, class 2 dot, or sometimes even class 1.0, class 2.0. It's pretty weird. I would have to make it a dot as type int. That means I'm gonna enforce this result to be an integer, and hence I'm not gonna have 1 dot or 1.0. It will be strictly a 1. So that's the reason. So I'm gonna make it to be, as dot, and then now I can just simply make a decision. So if y predict equal to 1, I'm gonna say decision equal to approval. Else, which means it's 0, then decision is gonna be denial. So now I can print the final decision. the decision for the test data or for the test applicant is decision. Okay, here we go. So you can see the decision for the test applicant is approval. It should be where it is. It should be same here. Training accuracy is 9 point what is the number? 9.65 data approval. Okay, so this shows an example. Of course, you can test a different data, of course. I mean, you can make it, for example, let's say I don't know your age, let's say 25-year-old, and then let's say, degrees I married or not, let's say suppose not married, and suppose the education level is, let's say if you finish this, I'm not sure, will they give you a master or certificate, but at least undergrad. And then the next one gonna be 16, I believe it's years employed. Let me see. Yeah, years employed prior default. Suppose the years employed is 5 years, prior default is zero. Let's say salary, I'm not sure. Let's suppose you have full-time job. Suppose your salary, I don't know, like 60 maybe. Let's say credit score is 700. Let's see. Okay, great. The result is still approval. Good job. So, okay, so this shows an example, to use the logistical regression in the real application, which is credit card denial or approval system. That's the reason you can see, it's so fast. And typically those things are in the back end. In the front end, it just pass those parameters, to the SQL to the database that you can use SQL to get those things, and then in your back end you can run the model, for example, LGR model, and then you get the result, and then send it back to the front end, and then tell you the decision. Uh, those kind of decisions typically takes the backend server maybe 5 seconds, but due to the internet speed or those kind of things, it has typically takes like 20, 30 seconds or 60 seconds. So you'll see. Okay, so that's everything about the logistic regression. Any questions? No? Okay, so then let's move forward. The last example, the last classifier that I'm going to introduce in this class is support vector machine. So here you can see we introduced one, two, three, four. Although only four what classifiers, I can tell you it covers most, I would say really most contents about the basic machine learning things. And you should be after this plus I have not uploaded plus lecture 10 and 11, which are, the k-means clustering and the PCA methods. You should be able to read many simple, materials and finish some pretty simple codes for a practical work. I don't think due to the time limit, we will finish, we have 3 more classes excluding today's class. I don't believe we have time for introducing, the neural network. But with this neural network, it's pretty simple. It's nothing, just a linear, Azure model. With this, especially the kernel trick that we're going to introduce today, you will be able to actually really do a lot of practical work in under the framework of machine learning already. Okay, so support vector machine is another classifier. The basic idea is here. So, oh, sorry. We have a fundamental question, which is, hey, given those data, class one, class two, how can we separate? Be careful, I use the term separate. How can we separate the two classes, here? Uh, a basic idea is that I want to drop a line, right, to split them so that, for example, I can have L1, L2, L3, L4. I can have those 4 lines to divide these two classes. And this line is called separating hyperplane. Why we call separating hyperplane, of course, in the 2D, it's a line. 3D is going to be what? A plane. 4D, 5D, it will be something. So to give it, a common name, we say separating hyperplane. The problem is not which hyperplane here should we choose? Which one is the best? Intuitively, we want to choose what? We want to choose a separating hyperplane that maximizes the distinction, the difference between, the two classes, isn't it? So this can like effectively separating them as clearly as possible. So intuitively here, I will choose L2, which is, looks the best. The problem is that you remember what when we introduced the linear regression, you need to accurately define the best. You cannot just description best. We need to have a mathematical model, right? And hence we do it in this way. So here we want to choose a separating hyperplane that maximizes the distance between the two classes along the normal direction of the hyperplane. So here, let me see. So this, oh, sorry. Suppose I choose this bold red line as the separating hyperplane. So this is the normal direction, right? What I want to do is, okay, the distance between the two classes. So first of all, I want to make this separating hyperplane without the loss of generality. I want to make this one in the middle. And hence, I want to draw plot these two margin. These two margin are what are parallel to my support hyperplane, and hence this direction is 90 degrees, normal direction. And here we need to define the distance between two classes of data is defined by the minimum distance of 2 points of each of the group. In other words, if we define in this way, the minimum distance between these two groups is going to be this point and this point. And later we'll see, I will call these 2 points as support vectors, which is exactly along on the margin. And then because this separating hyperplane is in the middle, so if I say the distance from this line to this point is r, so this must be r as well. Why? Because it's mirror, it's symmetric, it's in the middle. In other words, I want to find a separating hyperplane such that these two r is maximized. So that's the thing. So some terms here, two hyperplanes that touch the closest points from each class used to measure this distance are called margins. So these two are called margins. And the separating hyperplane lies exactly halfway in the middle between these two margins. And so here we are formally, if we give it a formal term, it's called hard margin SVM, or if you want to make it easy, just call it original SVM model. Later, we will formally define those, the whole model using a more practical method, which is soft margin SVM. We'll introduce it later, in slide 7. Here's slide 3. Okay, and I want to mention something here is that in some notations, the margins themselves are, defined or referred as support vectors. I personally don't like this notification, to be honest, because in my personal view, support vectors, it should be more clear, and these things should be margins. But just to let you know, because if you read some literatures or some papers later, if you're interested, you will see some people call this one as support vectors. Just want to let you know. So the entire framework, including the data, the separating hyperplane margin support vectors, is called the support vector machine (SVM) here. Okay, so in the next page, I will show how to derive the expression of this R because we want to maximize it. Okay, so first of all, we want to choose a separating hyperplane here to make my life easier. I just use SH to indicate the separating hyperplane that maximizes the margin with 2R. So I will first define the separating hyperplane to be WTX, W and X are vectors plus B is a scalar equal to 0. Okay, so now be careful, by the way, this 0 is a scalar as well. Okay, so and then I can name this margin 1, margin 2 to be the equations to be WTX plus B equal to -1 and a positive 1. And I know many people, if you have never seen this model before, you want to ask, so why? Why? Even if I admit that you can make this to be 0. By the way, make this to be 0 is always legal, is always valid. Why? Because it's 0, so I can scale it. You see what I mean? Say, suppose you want to, you can, let's say, times a whatever factor, let's say 3WT plus a 3B. So what my point is that it doesn't matter what is the number, but I can always scale it to make it in this form. The question is why, even if I admit this is valid, why I can also always validly define margin 1 and margin 2 to be WTX plus B equals to a negative and a positive 1. Why? Because, here, I believe I gave you an example. No matter what the original form, we can always transform the equation into this standard form, which is WTX plus B equal to minus or plus 1 by appropriately shifting and scaling W and B. So here I give you an example. Suppose the true margins are given by, so here to avoid notation confusion, I make it to be W0, W0 and B0. Suppose there W0 x plus B0 is 1 and the W0 T, I mean, this one here, I just randomly, define. You can define any number, the same trick, make it exactly the same thing. Now you can just, you can just solve, the coefficient before these two. Then we can convert this way. W, in the first equation, you just times 2. You see what I mean? So it becomes W2 WT x plus 2 B0 minus 2 equal to 0. And then in order to make it to be negative 1, what I can do here is I will shift it to make a negative 3 here. So what do you got? You're going to have, sorry, let's do this. Let's first time 2, both sides. 2WT, W0 TX plus 2 B0 equals to 2. And then minus 3. And hence this 2 becomes what? Negative 1. And hence you get this equation. You see what I mean? So let me underline it to make it more clear. So this one is equivalent to this one by just times 2 in both equations is minus and then minus 3. And then similarly to the other other equation, which was WTX plus beta 0 equals to 2, I can make it in this way. Similar things. Here in this equation, I times in this equation, I times 2 and minus 3. And then I will have convert this equation to this equation. Now it's easy. Why? Because I just simply need to denote W equals to 2WT and then B equals to 2B0 minus 3. So I'm going to convert this model to what? To the standard form again, which is WT x plus B equal to negative 1 and the WT x plus B equal to 1. That's it. So this is just an example to let you know it doesn't matter what is your original equation. I can always convert it to this standard form, which is WTX plus B equal to negative and plus negative and a positive 1. That's it. Okay. So now I have these standard forms. Let's derive let's derive this R. What I want to do is that I want to express this R, the distance, in terms of W and B. Why? Because W and B is my, the only thing. Once I know W and B, I know the whole system, right? I know the whole separating hyperplane. That's it. And also the margins due to the standard form. Okay, so how can we do it? What we can do is that, first of all, we just randomly take an X in margin 2. The same thing if you do it in margin 1, you can derive it after the class. I guarantee you the result is exactly the same. Okay, so here's X. Then I denote its projection onto this separating hyperplane as X, or I don't know how to read this, X pen, let's say perpendicular, X per is called. It's because it's X perpendicular to this, to this X vector, let's say X per. Okay, so I can write what? I can write X equals to X per plus, so I need to define this direction. Remember that this direction is what? The norm vector, right? The norm direction of this separating hyperplane. And I just need to know the unit norm vector. The unit norm vector, but by the geometry is super simple. It's W divided by the length of W, right? So it's W divided by 2 norm. I mean, 2 norm of W means the length of W. And what is the actual, this is the unit norm, this direction, but how long it is this? The length is R. Hence, I have this, I have X equals to, let me just plot a, so this, whatever X equals to, let me use another color, let's say blue color, X equal to X per plus this vector. And so how to express this vector? This vector, the direction is the, the norm vector direction. And hence I get the unit norm direction times the length. The step length is R. So I have X equal to X per plus W over W norm times, norm means 2 norm times R. Be careful again, R the scalar, okay? And then you just, times WT plus B on each side of the direction of the equation, sorry, then you're gonna get this one, WTX plus B equal to WTX per plus B times WT, W over W norm times R. Okay, so now let's have a look at, let me just clear everything. Then let's have a look at this. What is this side? What is this value? We already know that X is what? X is on margin 2. And hence, by the equation of margin 2, I must know my WTX plus, WTX plus B. This one must be equal to what? Must be equal to 1, right? This one must be equal, wait, let me write it. This one must be equal to 1. Sorry, it's just really it's just really ugly. But just to let you know, this is number 1. Oh, okay, I add a better 1. Okay, then let's have a look at this side. This side is what I have WTX, the WTX per, and the WTX per must be what? Must be 0. Why WT X per must be 0? Because what is your X per? X per is perpendicular to this X. You see what I mean? And hence, this is like inner product. Inner product of them must be 0 because they are 90 degrees. Okay. And then, actually, you know what? Sorry, my fault. I should not claim this is 0. I should claim this. Actually, there's a much better way to explain it. Sorry about this. Sorry, let me just redo it. So this one, first of all, this one must be 1. And then let me use another color, use this color, and this one must be 0. 0. Why? Don't forget that I have this. I have, let me see here. This point X per is lies on the separating hyperplane. It lies on the separating hyperplane. What is the equation? WTX plus B equal to 0, right? Okay, so here my X per lies exactly on it. And hence the whole thing should be 0. And now I get what? I get this equation, which is 1 equals to 0 plus this WTW as what? As norm square. Why? Because this WTW simply means the square of the norm. And this can, eliminate 1. And hence I get what? I directly get R equals to 1 over W norm. That's the thing. And this is a result for the margin. And what we want to do is to find a W which maximizes the R. So that's the idea of the original, be careful, I'm saying original or hard margin SVM. Here we go. So to maximize, we want to maximize the whole thing. So it's equivalent to what? To minimize the reciprocal. So why do we want to make it in this way? Because here, if we want to brutally minimize it, it's, we have something in the numerator denominator, which is more difficult. By considering, the opposite of that, we can, by considering the reciprocal of it, we can make it to be what? A quadratic problem again. Why? Because it's square. And hence, wait a minute. So, sorry. Here we want to equivalently, we want to solve the minimization of the reciprocal, and we add a square here because W norm is a non-negative. I would say in most cases it's non-zero. Zero is meaningless. Zero is the trivial solution, which is all factors are 0. It's a positive number, so it's equivalent to make to solve the minimize the W norm is equivalent to minimize half of W norm square. So why do we need to add a half and a square here? Because later you will see we will make the derivative or make the gradient so that this half and the square are going to be canceled. That's the reason why. And the most important thing is what is this constraint. So here we've already mentioned we will make y to be -1 if it belongs to class 1, and yi equal to +1 if it belongs to class 2. And people may ask immediately first, why do you want to make it to be this? Why don't you make it, for example, yi equal to 0 if it goes to class 1 and y equal to +1 if it goes to class 2? The reason because, as we just mentioned, we can, no matter, how does the margin look like, we can always use this, -1 and +1 as a standard equation. So under this framework, if we define yi to be -1 and y to be +1, we can just make it match the system. And mathematically, we will write this formula. It can make my mathematical model much, much simpler, easier. That's why I define this way. Okay, so you may want to carefully check this equation, this constraint. The constraint makes sense. Why? Because for each data point, let's say data point I, if data point belongs to class 1, which is here, right? Data point belongs to class 1. What do we have? So as we just mentioned, in this case, we'll have yi equal to -1, remember? And hence the whole equation the whole constraint becomes for a specific I, okay, becomes WTX, it's actually here, WTX plus B is less than or equal to -1. Why? Because yi equal to -1. So geometrically, WTX plus B is less than or equal to -1 means what? Means this part, right? Means this part. Let me use a green color. Yes, it's green color. Means this part. Why? Because this line is WTX plus B equal to -1. And you want to make it a less than or equal to -1. So of course it's this direction. And this makes sense. Of course, if that is the case, this is exactly class 1. This is exactly what we want. Similar things. What if, let's say, my yi, the training point, belongs to class 2? In this case, what do we have? What we have is this direction. Why? Because you will have 1 times this is greater than or equal to 1. In other words, the constraint for point I becomes WTXI plus B is greater than or equal to 1. So this line is WTX equal to 1. Greater than or equal to 1 means this direction. And hence, this is class 2. Exactly what we want again. So this model, the objective function with this constraint, be careful. The constraint looks one constraint. Actually, it's composed of n constraints. Okay, this means for each training data for each training data point I, you have one constraint. If you have n training data points, you have n such constraints. Okay, so this one expresses the whole model that we have. So now suppose we get a solution, which is W star and B star, be the optimal solution to this problem. Now I give you a target data point X. I want you to make a decision, to make a prediction. What label should it belong to? What we're going to do is we will compute the decision function, this one, fx defined by WTX plus B, exactly the same here. And then to see if this decision function value is less than 0, that means what? That means it lies on the left side of the separating hyperplane. Since here is the original model, or later was it's called hard SVM model for 2 classes, it's actually on the left side of the margin 1, actually. We will what? We will classify it, or we will predict it to class 1. Otherwise, if this function, this value is greater than 0, then it's in this direction, and hence we will predict it to class 2. So this is the whole system. How can we define it? And to solve this model is extremely simple. Why? Because it's a quadratic model. And I mean here it's not an optimization class, but just to let you know, it's super fast to solve this model. Okay, so everything looks good, right? What you may not know, or what you may not have realized here, is that there's a big shortcoming of this model, of the original SVM. Why? Because by doing this, we assume that in the training data, there's absolute no misclassification. However, the practical case is no. I mean, if you consider practical data, there's always some misclassifications. For example, consider this group of data. no matter how you try to define this separating hyperplane, there's always at least one misclassification data. For example, like if I choose the separating hyperplane in this way, so here you can see, let me just circle it. This one, let me just use red data, red point. This is a misclassification. This is a misclassification. I mean, no matter how you choose your separating hyperplane, this plane, you will always have misclassifications. Okay, then in this case, the previous model, the original SVM model does not work. Why? Because it never, let me remove it, it never considers the option, what if something, let's say, what if this data is here? What if this data is here? Misclassification. So we need to what find a new model to give a tolerance of those kind of misclassification. So the idea here is to address this issue. We try to modify the model of the original SVM to allow some training, points to lie inside the margin line or even be misclassified. So this idea is, introduced. This idea is actually soft margins, and in which we will relax those constraints and enable the model to tolerate some errors. This is the this is the modification for motivation. Sorry, this modification shows the motivation of the development of the soft margin SVM. Let's have a look at how we can make it. So first of all, the whole distance here is 2r equals to, as we just derived, equals to 2 over, W2 norm. Okay, so now let's consider, so in this system, I marked class 1, class 4, class 3, class 2. These four data are kind of like errors. Why? So for example, we can have something, in the correct side of the separating hyperplane, but inside the margin, for example, x2 and x4. You can see these 2 points. Let me still mark. Let me circle it. Okay, x2 and and x4. X2 is here. X4 is here. You can see x2 and x4. First of all, x2 belongs to class 1. I mean, this green triangle is class 1, right? So x2 is indeed class 1, and x4 is indeed class 2. Correct. However, there's an issue. Did you see it? The issue is that although they're in the correct side of the separating hyperplane, they are what? They are inside the margin line. So ideally, I want to have, all those kind of class 1 points here, but x2 is inside the margin line, similar for x4. So this is one issue. And a worse issue is actually uh, class 1 and class 3. Why I say they are worse issues? Because class 1 and class 3, they completely, go to the wrong side of the separating hyperplane. And hence these two data are completely misclassified, but they're really like misclassification. I want to enable the model to consider these two errors. How shall we do it? So to solve this issue, what we do is we introduce a new variable CI called slack variables. And we want to define the CI to be these kind of cases, which means if CI, so first of all, if xi lies on the correct side of the margin. So for example, all these, let me just, let me use another color. Let me, for example, use the red color. All these, okay? All these cases, these data points, they're all correct. So if they lies on the correct side of the margin, then I want to have this stack variable CI to be 0 for these data points. Then for those axes, for example, x2 and x4, for these axes, if they lies inside the margin, but still on the correct side of the separating hyperplane, I want this CI, the corresponding CI, which is CI2 here, and CI2 here, and CI4 here. I want these stack variables to be less than 0. Why? Because somewhat it indicates the distance here. So this the right hand side is 0 in the separating hyperplane, and the margin absolute value of the margin, the right hand side is 1. So you're between 0 and 1. So you should be less than 1. And in the worst case, which means a misclassification like X1 and X3. In these cases, what I want to do is, let me use a yellow color. Let me use a dark red color. These cases, where's X3, which is misclassification. Similar things. Again, the distance, this distance is the whole, this distance is 1. And then look at your x1, your Casi1. Your Casi1 is bigger than this distance, and hence your Casi1 should be greater than 1. Similar for Casi3, similar things. My distance here is 1. And then your Casi3, you can see here, it's bigger than this distance. And hence, I want to have your Casi3 to be greater than 1. So I want to create a model in this way. Then immediately, the question comes, how do we incorporate these slack variables into the model, right? Here, what do we say in this way? Okay, these are 3 cases. Here we mentioned these 3 cases as just what we think our target, but how can you make it in your mathematical model? Okay, then let's see the next slide. Here we go. We can define this model, and I claim this model perfectly matches the requirements here. Let's have a look at it, why it matches. First of all is the objective function. So we can see this part, this part is, let me use another color. This part is, the same as the original SVM model. What is added is this item. This item is called, or this term is, let me remove it. This is called the penalty term, where this C parameter is called const parameter, or you can call it regularization parameter. It's greater than 0 or greater than or equal to 0. And this is actually a trade-off. First of all, Casi is non-active, it's greater than or equal to 0. And don't forget one thing, that our target is, our objective function is a minimization problem. And hence, what's going to happen? The problem itself will always choose a small part, a small Casi. Why? Because is non-active. So of course, if Casi I can get a 0, I can choose 0 because C is non-active. If suppose Casi, I can Casi I, for example, is feasible. Let's say 0 is feasible to Casi I. Of course, I will choose this 0. Otherwise, suppose I choose Casi I equal to 0.1, then it violates my minimization target. You see what I mean? And hence, under this setting, in which Ci for all i's are greater than or equal to 0, the model itself will always try to choose a c-value as small as possible. So this is the thing. And here we can see the part sigma I from 1 to n in Ci, this is actually what? It's actually a penalty. It tries to smaller your Ci, and C is a like hyperparameter. We call it train maximizing the margin. So this item is to maximizing the margin, and this item is to minimize the classification error. So this is the thing. So why can we claim that this model perfectly matches these 3 requirements? Let's just consider 3 cases. Okay, first of all, if x lies on the correct side of the margin, meaning that x is something like this, something like let's say these points. So what's going to happen is Casi equal to 0 is achievable. By the way, why Casi equal to 0 is achievable? Because you can simply substitute Casi equal to 0, and then this constraint, let me just, and this constraint is still satisfied. So my Casi 0 is achievable. Of course, if Casi 0 is achievable, since this is a minimization problem for the corresponding, I of Casi I, I will get it. I will take Casi I to be 0, right? Because it's a minimization problem, and again, C is greater than or equal to 0, and the Ci is greater than or equal to 0. Okay, so now let's have a look. What if Casi, what if let's say Xi lies inside the margin, but are still on the correct side of the separating hyperplane? For example, here it's like x2 and x4. Let's just, without a loss of generality, let's have a look at x2 only. So for x2 itself, you see it. In order to make this equation, let's have a look at x4 because why? Because in the setting of x4, y4 equal to 1. So we will have wt x4 plus b. And now I can no longer get c4 equal to 0. Why? Because if I set up c4 to be 0, it doesn't work. Why? Because you cannot say y, what I'm saying. But you cannot say WT x4 plus b is greater than 0. Why? Because if it's indeed greater than 0, you should have something here. You should have something here. You see what I mean? Unfortunately, the truth is your x4 point is here. And hence, you know what? The right-hand side, 1 minus Ci, it must be between 0 and a positive 1, isn't it? Then you just solve it. 1 minus Ci is less than 0, or is less than 1, greater than 0. What you get? You get Ci is between 0 and 1. See it? It exactly, satisfies our, requirement here. Ci is between 0 and 1. Here we go. And the last case is, what if xi lies on the wrong side of the separating hyperplane? So for example, let's consider, let me just remove everything here. For example, consider x1 and x3. They're completely on the wrong side. Let's say x1, because, x1, the y equal to 1. So if you substitute it, you will have wt x1 plus b is, versus 1 minus c 1. The problem is what? The problem is that this number must be less than 0. Why? Because here the separating hyperplane is wtx plus b equal to 0. And now you're on the left side of the separating hyperplane. And hence, if you want to substitute into this, which is wt plus x1 plus b, x1 is here, the result of the right-hand side must be something negative. You see what I mean? And hence, I must have the right-hand side 1 minus xi must be in the correct side, which is a contradiction because I know x1 is already in the wrong side, and hence I must here c1 is less than 0. And you just solve it simple, you will immediately get c1 is greater than 1. See the requirement here? If it's in the wrong side, I want to have ci greater than 1. Again, it perfectly matches the requirement. Hence, I can claim that this model is exactly the model we're looking for here. It satisfies all the requirements here. See it? So we get this model. And we name this model to the soft margin SVM model. So, I just realized I moved this point a little bit. Sorry about it. So this is the thing. Okay, there's something I want to mention here. To balance margin maximization with tolerance for some misclassification or margin violations. And this is controlled by what? This controls the trade-off between these two targets, which is to maximize the margin and to minimize the classification error. And the second thing I want to mention is, why do we call it a soft margin? Soft means this margin. Maybe I should use dash line instead of solid line for this because Zoom doesn't provide me a dash line, but just to let you know, it will be something like this, a dash line. Let me just clear all. Because it allows, the margin to be soft. So the margin now becomes 1 minus Ci. See it? And this Ci is the slack variable, allowing some flexibility. Hence, we call it soft margin. By comparison, the original, SVM is somewhat like the hard margin, meaning that absolutely it doesn't allow any violation of those misclassification. Well, it's a good idea, but it's not practical. You see what I mean? And hence, when we say SVM model, what we always refer to is this for two classes, okay, is this soft margin because it's more practical, it's useful. It's not like this good model, but not useful. So that's the thing. The next thing I want to mention before we define here, points lie on the margin as support vectors. Okay, in the definition, misclassified. So for example, here in this, example, x1, 2, 3, 4 are the support vectors. Okay, and similar things. How can we make a decision? Let W star, B star, and C star be the optimal solution to the soft margin SVM model. Similar things, we define the decision model in this way, W star TX plus B star. And then if this FX is less than 0, that means what? That means it's this direction, right? And hence we classify it to be class 1. If it's greater than 1, then it will go to this direction, and hence we will predict it to class 2. So this is okay. And then how do we choose a fee, or let's say what is the impact of the different values of a fee? So if a fee is a large value, this means what? This means I will have a high penalty for having those non-zero slack variables here in the objection function. And hence, what's going to happen is that the margin will become narrower, will become very small. Why? Because the penalty of a misclassification or in the wrong side of the margin is going to be very high. So I will try to, make a more conservative SVM, make the margin smaller to eliminate, try my best to eliminate such, errors. Errors means two types of errors, means either misclassification or something inside, in the wrong correct class, but inside the margin. So the result will be this. The distance between margins will be very small. As a special case, the harder margin of the original SVM model is the case of C goes to infinities, right? Which means I absolutely do not allow any misclassification. And hence we say it's not practical because given a practical training data, how could it be possible that it's not, there's zero misclassification data? And by contrast, a small value of C here means I can tolerate, means a pretty low penalty for having such, non-zero slack variables, meaning that such errors. That means, okay, I can tolerate error. The margin is going to be relatively big because I can tolerate, such errors, two types of errors again. Misclassification like class 1 or something like class 5 and class 2, which are inside the margin but still in the correct side of the separating hyperplane. Wider, let's say, compared to the okay. So these are things we introduced the linear SVM model for the two classes. Here, we need to consider what if we have more classes. Here, I will just make it easier, because the corresponding things are pretty similar to the two classes case. So we have typically two classes of models. The first is called a one against all model. But the idea is to build M submodels where each submodel separates one class from all the other classes combined. Another model is called one against one model, which is to build M choose two submodels. Each submodel separates a pair of class. And hence we have, each, let's say class K is versus class K versus class L. And hence how many submodels we totally have M classes. So it is M choose two such pairs. One thing I want to mention is that the logistic regression model introduced in lecture 8, is actually a one class against all against all against. I should say one. It's a one against all, not all against one. I actually get confused. 1 minute. It's a one against all approach. Actually, all against one, the same thing. Why? Because it's all other classes in the group against the last class. Remember how we model? Let me see where is the logistic regression. Let me just open it. I should not have closed it even. Here, look at the model. uh, okay, let me open the local one. It's a bit too slow. Local ones here. Okay, look how we model it. We will have all other classes against the last class. See it? Everything against the last class, and hence it's actually an all against one. But here, actually it's a one against all. But here, all against one is also correct. Why? Because it's the first thing is all, then against. So I mean, I would say it's all against one approach. So now let's have a look at how do we model these two cases, all against one, one against all and one against one. In the one against all SVM model, first we will choose the case class as a reference. So we'll use K class K against all other classes. The objective function is still the same, but the constraints becomes this case one, if the training data I belongs to the label of training data I is K, then we will still have this which is the same as this model as the original soft SVM model. However, if the label of the training data I is not equal to K, I will model it in this way. So basically what I do is I will just, remember the one I before it, I will just, even if you have how many M classes instead of two classes, I will still consider, this one I to be positive one or negative one. Positive one means the training class, the class of the training data is K. Negative one means the training data, the label of the training data I is not K. And hence you can see if I plug in y equal to negative one, I get what? I will get negative of this as less than or equal to negative one plus K, right? Which is exactly here. You see what I mean? So that's the thing. And the KR is greater than equal to zero. In other words, one against all means what? Every time in every submodel, I just consider its two classes, which is K or not is not K. That's it. And so I can use the idea of two class, soft margin SVM model to model it. And be careful, this is only one submodel, okay? And there are m such submodels. Why for each class? Because every time I can, one against all, right? So this one can be class one. So I have one model. Class two, I have one model. Class M, I have one model. You will have m such submodels. Okay, so now let's WK star, BK star, CK star denote the optimal solution to the case submodel. So I will have, I will what, for target data X, I will predict its label by this way, which is the maximum, the maximum of, the value substitution. What you're going to do is, so now you already get all these parameters, right? And then you also get this target data X. You just substitute inside. And then which one gets the maximum value of the decision function, you will classify this target data point to this class. So this is the meaning. So here I wrote, we assign X to the class K, label K, whose decision function is the largest. That's what we do. And it's very, very easy to see in the case M equal to 2, which means we have two classes. This model is equivalent to this model, of course, because of basic ideas. It's exactly plug it, one negative one inside. That's it. So this is very simple to understand. This is one against all SVM model. The second one is one against one SVM model. So the idea here is instead of one against all, I'm gonna make one against one, which is I'm gonna choose a pair of KL. So KL are both elements here from one versus two, one versus three, one versus four. I mean, here, be careful, I'm saying pair. So one versus three is equivalent to three versus one. You don't have to one versus three compute it one time and then, three versus one, solve the model one time. No, they're the same thing. Okay, so how many such pairs we have first? Totally M classes, we choose two. So we have M choose two such submodels for all these KL pairs. Second is if I've decided KL, so what I'm gonna do is that I'm gonna make y equal to k to be the case of in the two class cases y equal to 1 and the y equal to sorry, I should say this. So if the training data of data, if the label of training data point I is k, sorry, here is k, then I'm gonna substitute to the case which is here, y equals to positive one. And if the label of the training data I equals to L, then I'm gonna plug in y equal to negative one. In other words, here, what I'm gonna do here is I only consider the labels for K and L. Then I will solve one submodel, another pair of KL. I solve another model. You see what I mean? So that is a method to convert M classes to be two classes. Two classes is only K and L pair. Then I'm gonna have M choose two, which is M times M minus one divided by two, such sub model. So let me just write it down in case. So this one equals to M minus one times M divided by two factorial, which is two. So I'm gonna have so many submodels. Okay, again, let W star KL, B star KL, and C star KL denote the optimal solution to get above one against one, not is it one against one? So sorry, typo here. Here's one against one SVM model. Then for target data point, we will define the decision function again like this. So we add one vote to class K if this FKL is less than zero. Otherwise, if it's greater than zero, we add one to class L. We want add one vote to class L. So now if we do all of these pairs, so for each class, there will be a score, right? One vote, one vote, one vote, one vote. There's going to be a score. So I will predict, this target data X to the class label, which has the highest score, the maximum score here. That's what we do. And again, if m equals to 2, it's easy to see that this system is exactly the same system as our soft margin SVM model here. So these two things will be exactly the same. So these two are the two ideas of handling more than the case for more than two classes, one against all and one against one SVM model. Okay. The next thing I'm going to introduce is what is the kernel trick. The motivation of kernel trick is so before, no matter hard or soft margin SVM, again, without a loss of generality, let's consider two classes only. We only use what we used only, you can see these cases are always what? Are always a line. Line means what? No matter separating hyperplane or the two margins, they are lines. That means what? That means they are linear margins, linear separating hyperplane, right? However, in some cases, like in this case, the original data is this way. Linear may, of course, first of all, linear works, but it may not be the best option. For example, in this case, if we can make, the hyperplane like this way, then clearly the result will be better than the linear SVM. And this is the motivation of the kernel trick. What we do is we will reformulate the SVM model. Again, we're talking two classes. So what I'm talking about is this soft margin SVM model for two classes. We will rewrite this model. And then by the form, what you will see is that I will replace the input covariate in a product vector here by a kernel function. Let's see how do we do it. First of all, we can rewrite this model, use the dual form, and we can make it this way. This is a bit complicated. I mean, it will take some time, really. I mean, to introduce the dual and the form and then make an equivalence claim. If you're interested, just where did I write? Here. If you're interested, you can see section 2.2 of this extensive reading part. I show a way to prove why this model is equivalent to this soft margin SVM model for two classes. Okay, so now from where it is from this model. By the way, this model is called a dual SVM formulation or dual SVM model. We can see that this part, it's just a format of inner product. And also, if we apply this model, then the decision function will be correspondingly expressed or changed to be this way. And in the decision function, you will also see that the xi and xj, which are the training data, also appears in the form of the inner product. Then we immediately have an idea because inner product means what? Means I don't care what is exactly xi or what is exactly xj. What I care is the inner product itself. So the kernel trick, the idea is I'm gonna replace the inner product of this one by a function of training data xi, training data xj. So I will have a new thing. And the further, since it's an inner product, so who cares what is the function of, explicitly computing hxi or hxj? I don't you explicitly compute it. What I need to do is I just need to define a function of k xi xj, which is this. That's it. And hence, we can have this. The idea is I will replace all these finally, I will replace all these xi, xj inner product by a function of k, xi, xj. This k is the kernel. And that's the kernel idea. There are four very, very popular kernel functions. The first is called Gaussian kernel. It's also called RBF kernel, radial basis kernel, but I mean, personally, I call it a Gaussian kernel. Why? Because that's nothing but a Gaussian function here. And it all often delivers excellent results in practical applications. And this is the most widely used kernel. The second one is the linear kernel. And if we set this, shift parameter R to be 0, then the linear kernel is equivalent to the standard non-kernel SVM, which is a soft margin SVM. The third is polynomial kernel with degree of t degree p. So you can see this is a polynomial function with degree p plus the shift parameter r here. And actually, I should make it to be gamma instead of r. Yeah, because in scikit-learn library, this number is always gamma. But here, but here is an issue because here it has two parameters, both the scaling parameter and the shift parameter, and this is a sigmoid kernel. It's also called a neural networks because neural networks we basically we're running sigmoid kernels here, and here the tangent h function is the hyperbolic tangent function defined in this way. The good thing is that in the scikit-learn library, you don't need to know, I mean, explicitly compute this. It's all built in, okay? But you do need to know the idea of, let's say one against all and one against one idea to handle more than two classes. And the most important thing are two things. First, the model of the soft margin SVM, why this model is derived in this way, and this model perfectly matches this. And why do we require this? And the second thing is the kernel idea, which is I don't want to have a linear separating hyperplane and margins. I want to have curved things. And hence, by rederiving the model, we have the inner product. And then first, we change the inner product to be a function, hx. Now, then we write the whole inner product as a function, which is the kernel function. So this is the idea. Okay, now we can start coding. Now we can have a look at the things. I know some of you may question, so why do we need to know those mathematics? The reason is because if you know those mathematics, you can actually judge how or predict how a classifier works for a classification problems. And you will know the basic ideas of everything, how everything works, instead of just brutally use everything. So, okay, in the first example, what is that? Okay, in the first example, it's a SVM, and let me just do it by to cheat. Let me just put it to cheat because some parameters. Okay, so let me just come here. Here. Okay, I better close it, and I can close the kernel here as well. So this is actually a kernel. Let me close it. But we now want to close kernel just in case, if I make a mistake in lecture 9 if I write x equal to 1, then it may use the x from lecture 8. Then it will call the error. So that's the reason. Okay, so first of all, I want to show the line numbers. So I'm going to import numpy smp import matplotlib pyplot as plt. And then I'm gonna from matplotlib dot colors because I will, make those, where this, I will make these decision regions. And hence I need to make this listed, map, need to have this, listed, color map, import listed colored map. Okay. And from sklearn.svm import svc. So support vector classifier. Here, since the subplots here will be pretty big, I want to drag it, and hence I want to make this, the matplotlib IPY MPL, so that I will have a geographic, have a GUI control of it. Okay. So now, first of all, I will generate the Gaussian distributed training data. I have x1 equal to mp dot random multivariate normal parameters. Let me comment and paste. And I cannot have to manually put. Okay, I hate it. 236, and the sample size is 100. So y1 gonna be once x2 equal to parameters -5, 4 to 240. Have 120 data, y2 equal to 2 times mp dot ones, 120. Okay, now I'm gonna concatenate x equal to mc dot concatenate. Let me see here. X1, X2, x is equal to 0, meaning that I'm gonna concatenate it by rows, and y equal to mp dot concatenate y1, y2, x is equal to 0. Okay. So now okay, everything's good so far. So I can just print y, for example. You can see y just one and the twos, and the x's are just, those coordinates. Each data point is a 2D coordinate. So after it, we will just, plot it. Okay. In order to plot it, let's first generate a Nash grid. So I will have line space here. Here, let me see here. My parameter is dot main minus phi. Here, I'm just, cheating. Minus phi, and then x dot max plus phi. And in my example, I use the 200 points. Oops, sorry. Where it is? Here we go. That's great. Okay, so now I can define the decision region color. Color equal to listed color map. Now our color is a light coral and a light blue. Okay. So now, sorry. In my example, I use a light green, light blue. Actually, why did I use light blue, green? Interesting. Anyway, okay. So now after this, we can what? We can start the SVM training, right? So now here I'm gonna do in this example, just to let you know, I use the linear. I didn't use any kernel trick. I use a linear function here, linear SVM here. So I'm gonna have linear SVM training, and also make the subplots. Okay, so I have a C list first. The C list means, remember in our model, alpha is alpha C regularization parameter, remember it, which is here I'm talking about the soft margin. So I have this C. So I want to test the model performance under different C values. Okay. So my C values here are what 0.1, 1, and 5. So this is a list of C's. Regularization, let's say regularization parameter C's. Okay, so now what I can do is for each C, I'm gonna, make a fit and train the model and then make a subplot. So here I have for IC in zip, still remember what is zip? So the second thing is C list, of course. The first thing is what? So for each I will have something like this. So I will have a range, right? Range of length of C list. So what I'm gonna do is here, first of all, is to train the linear SVM model. So model equals SVC. Here, SVC, okay, here we have the kernel. Kernel by default is RBF. And the C by default is 1.0. But here I don't care. I just want a C equal to C because my C is, in the loop. So I'm gonna have kernel equals to linear and then C equal to C. Model dot fit xy. Okay, this is how we train the model. Now I want to plot the training data. The training data, which is first of all, I wanna show how many subplots per row. So here I have number of subfig per row is two. In other words, each row I want to have plot two subfigures. So I'm gonna have here num subfig per row equals to 2. And then I'm gonna create a subplot, right? So I will first have PLT. Oh, wait. I just realized, sorry. I should have here. I will first have figure equal to PLT dot figure. I want to create one figure, and now I'm gonna have the subplots. I'm gonna have x equal to figure dot add subplot. It's gonna be okay. So I need to determine how many rows and how many columns. What we know is that the number of columns is this, number is 2, subflag 2. So in order to determine the number of rows, what we can do is first of all, I need to see how long this C list is, meaning that how many C I'm gonna consider, well, which is just a length of C list divided by number of sub what. The problem is what? The problem is that this number may not be an integer. So I want to force it to be an integer. And be careful, here I'll have to use a ceiling function instead of the int, because int from f2.5, it will make it to be 2 instead of 3. What I want is if it's 2 point, let's say, suppose you have 5 C's, 5 divided by 2. Each row you want to put a 2C, right? So you need 3 rows. Why? Because it will be, the last row will be only one figure instead of 2 rows. And hence you need the np dot ceil function. And another thing is you need to brutally force it to be an int. Otherwise, it will be something like 3.0 instead of 3. But here, when we use as subplot, the parameters here must be an integer. And hence, I force it to be an integer. Okay, and also here will be I plus 1. I plus 1 is because here I is in the range of this. When we say range, it's what? It starts from 0 and ends at this number minus 1, and hence I will make a plus 1 here. Okay, so now I'm gonna x dot plot, and then I can just plot the first, x1. And the red dot, and then a label for training data 1, training data plus 1. Do the same thing for plus 2. Okay, so now I can make this so it will be just the what the plots. We can let me have a look at it. Let me see whether I can make it here. Let me see. Let me see whether I can run it here. Let me give 1 second. I will set a title. I will make it because I still have a lot of things to fill here. Set title. Let's say SVM with linear kernel at C equal to C. And then I already fit it so I can put the training accuracy as well. I will training accuracy is model dot score. Okay. Okay, here we go. So here I have not, that's why I want to make it a GUI. You see what I mean? Because it's so small. So because here in this semester we're teaching we're learning something directly using Anaconda server. If you install the Anaconda in your local machine, then it's super easy. You just use this magic Qt, that will directly show a GUI. But since it's on the server, I have to use this. So I have to drag it to make it bigger. So for example, you can already see the codes here. Here, of course, here I have not plotted the what the SV, the support vector. I have not circled the support vectors. I have not plotted the hyperplane, separating hyperplane. I have not, plotted the margins as we did here. But here, I just want to have a quick view of all these things. That's how we're doing here. Okay, so now go back. Let's add more things to our current code, which is I want to circle. First of all, I want to plot the decision regions. Then I want to circle the support vectors, which are the vectors inside, remember? And then I want to plot the separating hyperplane and the margins. Let's see, how can we do it here? So first of all, I want to plot the decision regions. So here I have x dot scatter. And we are gonna have, oh, wait 1 minute. Sorry, my fault. Decision regions. I will have y predict equal to model predict transpose. And then we're gonna use the rebel function to squeeze it to a vector instead of a matrix. Okay, so now I can make the p color mesh and then convert the size back, convert the shape back. Color. Okay, so this is how we make the decision region spell laws again. Decision regions. Next, we want to circle the support vectors. Circle the support vectors. Okay, what we're gonna do here is to use the scatter. So what we do is scatter. We make the size of the scatter to be very, very big. So it won't be a point. It will be like a big circle. So what we are gonna do is x dot scatter model dot. So since it's SVC, so it has something, Python has already computed it for you, which is support vectors. But the support vectors is really, really, it's really, really a vector, like it's a 2D, the first one gonna be all the x-axis. The second one will be all the y-axis. Why? Because my training data is 2D. And hence what I'm gonna do is this 0 means the x-axis, x, coordinates, and then model dot support vectors. Yes. And then this is the y coordinates here. And then here's the trick. I make S, which is the size, to be very, very big of this scatter. And then I have line width equal to 1 to make a line smaller, to make it a lines very, very thin, like this, very, very thin. Otherwise, it will be very, very big and it will cover my other points. Line width equal to 1, face colors equal to none, so that there will be no fill colors. And then edge colors equal to blue. So this is how we can circle all those support vectors. Then next, actually, we can just have a look at it, in case of P, AX dot. Okay, here we go. And you can see that, we've already circled all those kind of decision support vectors, and also we have already filled the decision region, right? The next thing I want to do is to plot the separating hyperplane and the decision and the margins. So here plot the separating hyperplane and the margins. Uh, to do this, first of all, unfortunately, scikit-learn library doesn't support, doesn't generate it directly. So what we're gonna do is that we will manually create, the points, and then remember the separating hyperplane, and also the what is something we building this way. Remember it plus be equal to positive one and the negative one, right? So what we do here is that we use the model fit itself, and we are gonna use where is we're gonna we directly put in this coefficient, because after all this is a linear model. I put in the coefficient inside and I plug in all the xx1, xx2, and now I plus model intercept, and then I use ax.contour make a brutal shift. The shifted to be -1, 0, +1, meaning the left margin, the hyperplane, separating hyperplane, and the right margin. So that's what we do here to force it. Okay, so first of all, I need to generate a V, which is a coordinate for the separating hyperplane and also the margins. I'm gonna have MP dot MP. Then I'm gonna brutally, make it for A in range. I'm gonna build this ZAB equal to, oh wait, did I? Yes, I already make an empty matrix model dot coefficient. So it will have 0, 0, and 0, 1. 0, 0 times x1 AB. You see what I mean? So here I brutally constructed first model dot coefficient 0, 1 times x1 a sorry, x2, not x1, x2 AB plus model dot intercept. Okay, so this is, we built the Z. After Z is built, I use ax dot contour, and the colors equal to blue. Let me open the cheat sheet. Okay, levels equal to -1, +1, 0, and a +1. This is brutally, I want to move it towards this part. And now I have an alpha to make it not too dark. And then line styles equal to these three line styles, which I remember one dash and double dash, a double dash and a one dash. So this is double dash, this is a one dash, that means it's just a solid line. Double dash is a dash line. So, and then I can run this, and yes, and then I just add ax dot set dot legend. Okay, here we go. Okay, so now the support vectors are all cycled, and also the margins and the separating hyperplane were all plotted. That's how we make it actually. Whew. Okay, so this is one example. Some important points are, first of all, a trick is here. I use scatter to circle it. Basically, I just plot a very big circle, make, there's no fill there. You see, I use size equal to 100 and the face color to be none, so that it's a big circle plus there's no fills here. Line width is one, make it a thing. So that's a thing. And the second trick is in order to plot those supporting hyperplane and the what and the margins. I actually don't know why in the scikit-learn SVC package, why doesn't it include it inside? Like, remember how we wrote a class, right? You can make this to be two class attributes, so that I don't have to manually make for A in this, for B in this, build this Z and plot it. But since it doesn't manually do it, and then finally, which part. Oh, this is one example. In this example, we use the linear support vector machine. And one thing I do want to mention, you can see here C equal to 0.1, C equal to 1, C equal to 5. Do you see what happens here? The margins is like tighter and tighter. When C equal to 0.1, the margins are relatively wide. now smaller the distance between two margins. And this shows what we just mentioned here, which is a big margin. Which is a small, where it is, which is a large value of C makes the margins conservative, meaning that they are tight, the distance of them is very narrow, tight, and a small value of C makes the margin more aggressive. They are wider. The mathematical reason is very simple. You just observe the what objective function, then you get it. Okay. So then in the second example, this is a building data set in scikit-learn called a MOVE. So I'm gonna run this one. I'm gonna run this sample, and then the point is I want to show the kernel SVM. Okay, so let me just move it. Let's go to the next example. First of all, let me just copy and paste those things. Okay, so what do we have here? I want to have one more thing, which is from scikit-learn dot datasets import make moons. Make moves. Okay, let me see. Do I have all the things? Yes, looks here. So first of all, I'm gonna generate the training data and the plot plot them. Let's say. Okay, so I have x y equal to make moves, and then n sample equals to, in my example here, I can see I use 1,000 noise equal to 0.2. I will explain what does noise equal to 0.2 mean. So first of all, let's have a look at x and y. First of all, let's have a look at y. And you can see y's are 0, 1, 0, 1, 0, 1. Because, if you come here, 0 means, I don't know which one is 0 actually, but one of the class is 0, the other class is 1, something like that. Okay, and also I can have a look at the x. X are nothing but the coordinates, you can see. These are the coordinates. Okay, now what I want to do is, because I want to get the axis whose labels are 1, zeros, and I want to get the axis whose labels are 1. So I want to separate them. And hence what I'm going to do here is create a list called class 1 list. Class 1 list means I'm going to get the indices of all the data x whose labels are 0. So remember this for I in range of x dot shape 0. For this, if yi equal to 0, then I'm going to put the indices to class 1 list. And also class 2 list is the same thing, as you just changes I equal to 0 to yi equal to 1. So in this case, I can simply write x1 equal to what? X of class 1, where does class 1 list? And similar things. X2 equal to X of the class 2 list. Okay. Now I can just make a plot. I'm gonna say plt dot create an empty plot, and then plt dot plot x1. Oops. Okay, so we can see it's like this way. Now let's introduce what does this noise mean. Say suppose noise is 0. You can see they are just perfectly like that's why it's called a moons, like making two moons, perfectly like this way. And then if I make a noise equal to 0.1, you can see it's bigger, it spams, you see what I mean? Spams. And then if I make noise equal to 0.5, you're gonna see it's gonna be like pretty chaos. And that's why I use those. I use noise. I believe originally I said, yes, I set noise equal to 0.2 because I want to make it like more practical instead of a perfect training data, right? And you can see, indeed, we have some misclassification points here. That's what I'm looking for because I don't want to have something like overfitting, Okay, so after this, I'm gonna fill something between, around here, right? So first of all, I'm to train the SVM model, and also I'm to choose different kernels, right? So what I'm gonna do here is, first of all, here I'm gonna let me first let's say data, training, or plotting, I should say, plotting and training preparation. So I'm gonna have x1 equal to empty dot length space and x main minus let me do it 0.1. That's the parameter I set. Here I just again you may ask me, so why is that a 0.1? Honestly, I make a trial. Maybe in the beginning I set it -1 and the printing result is not that good. You know what I mean? So I just gradually trial to make it a 0.1. But honestly, these are not really the most important. These are not that important because even if you just write mean, you don't minus it. So what? The problem is that the plotting edge is gonna be here. So that's the reason why I want to leave a small space, and that's the meaning. Uh, plus 0.1, and I use the 200 data points. And then here, 0.2. Sorry. I realized here's, oh, no, here's correct. Use this. 1, 200. Okay, so, well, one more. DR color, listed map, and then light coral, light blue. Okay, so now I can start like train and plot the SVM model under different kernels. Okay, so wait, kernels. So first of all, I will create a new figure. And I'm gonna first of all have a kernel list equals to, so here, this is gonna show all the kernel parameters. So I'm gonna have RBF, polynomial, and also sigmoid. And then I'm gonna, have a kernel. So here, let me think about this. Why do I, why don't I write it here? I'm looking at my code. Oh, okay. The reason here I don't write a zip is because inside the kernel you will have another inside the kernel, you will have another list, which is a gamma list. Remember here in my four kernels, each one has a gamma. I believe in the scikit-learn library for this sigmoid kernel, it ignores it ignores this number. They set this number to be. I'm not pretty sure, to be honest. Let me just search it, sigmoid kernel or SVM sklearn. So I have let me see, plot with different SVM kernels. Okay, here we go. Come on, RBF kernel. No, I need a sigmoid. Sigmoid kernels right here. And okay, here we go. So wait, so the gamma controls. Okay. So actually, this one has another coefficient, which is COE coefficient 0. But here I just use a default. So I don't know, default is, let me see. I'm actually not sure that the default value is what. I'm not sure the default value is what, but here I'm not going to control the R. Instead of I'm going to control the gamma, and hence I said here, let me change it after the class. I will make it to be gamma instead of R. So now let's go back to our coding. So I have this one. I define it. Let me put it back just in case I make any mistakes. I define R. Let me see here. I define I to be the subplot index for kernel in kernel list. If f kernel equals RBF, then because I here have a different gamma list equals to 0.1 1, 10, 100. L if kernel equals to poly, then my gamma list equal to 2, 4, 6, 8. Else, meaning that if it's sigmoid kernel, then the gamma list equal to, let me see, what did I put? 0 0.01, 0 0.1, 1, 10. So now I have the gamma list. I can really make the gamma for gamma in gamma list model equal to SVC, kernel equal to kernel. Where did I use kernel? Yes, and gamma equal to gamma model dot fit xy. Okay, so here I can plot the training data and the decision regions. First of all, let me plot the training data. Plot. Wait, did I add? Yeah, figure array. Add a subplot. Let me see. Here would be the length. The number of rows going to be the length of kernel list. Number of column will be the length of gamma list. And here the I. And my I start from 1, so I don't need I plus 1. And AX dot plot. Then it's just easy. Here's R. To save the space, I'm not going to put the labels here. B, and then I'm going to plot the decision rating, so I need to make a predict first. Okay, so one thing I do want to mention here, I applied a trick, which is a test. So where it is? Okay, so here the reason because it's pretty crowded. I just want you to write everything on the top, on the title. I want to put the training accuracy here, and hence I use this one to put the training accuracy in the bottom right corner. If you're interested in the syntax of ax.test, you can just search it and read the documentation of it. Okay. Here, oh, sorry. Here, here I will directly, apply it. Here's the what where you want to put this text box. So I put a maximum in the horizontal and a minimum in the vertical. And this means it's going to be the right bottom right corner. And this is what you want to put. So what do you want to write there? What I want to write is model.score, which is the training accuracy here, and the size equal to 12, and horizontal, wait, I don't have, okay, horizontal alignment. Let me see, I just want to make sure horizontal alignment equals to right. So in this way, it will write the what, and I follow the access dot set title, which is kernel at gamma equal to gamma. Okay, here we go. And finally, don't forget one thing, I plus equal to 1. Otherwise, it will cover. It's running. Take some time to run. Okay, here we go. So so this is the result, and I'd better not PRT dot legend. I'd better have this. Let me have a title layout, make it more clear. Okay, so as you can see here, we have, whoa, 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 wait. Okay, I know why it's wrong. This must be, I didn't put a dot. I must have, I forgot. Oh, here we go. I forgot the dot must be. We can just directly use this. Okay, here we go.
I can't see anything on the screen.
What, you cannot see anything? Oh, sorry about that.
Yeah, it's all black.
Oh, sorry. I don't know why the shares removed. I don't know how long have you, wait, don't tell me during the whole step you didn't see anything. Let me see. Can you see it now? I just reshared.
Yeah,
Sorry about
it switched back. I was seeing it before. It just all of a sudden went black.
Oh, okay, okay. I guess I accidentally clicked something to move the share. Sorry about it. Okay, now you can see it, right? Okay, but oh, good. You know what? You actually didn't see many of my mistakes. Okay, thank you. Yes, now I'm sharing, correct. Okay, so now you can see it shows the results, and you probably see why the. Let me put this one. Where's my PPT? You probably see why the Gaussian kernel is used most widely. You can see the result is really, really good. You see, for example, at this result, the accuracy is 98%, 0.3%. And by comparison, for example, you see probably, among different results, and also or the sigmoid, you see it's not that good to see it. But for the gamma equal to 1 in the RBF kernel, it's really, really good. And hence, that's the reason why RBF kernel is the most widely used. However, be very, very careful of overfitting, okay? For example, here, those kind of things looks more like overfitting instead of a real good results. In person, I would say this one is absolutely the best instead of this one, although the training accuracy is better, but it clearly shows, overfitting this is. Okay, due to the time limit, let me see here. I guess I will put this example in the next class, which is a real hand return example. And then on Thursday I will write a real number, and then we can just make it a real test, live test there. I do want to mention one thing. I guess I guess I will add one more example. I do want to mention one thing, which is homework two. So I've already received most of you, although not all of you, most of your homework here. Let me open homework two. Make sure I open the homework two instead of the solution. I know I don't have it in this computer. But anyway, so what I'm going to do is that I will add one more example, I believe, which is to compare the different classifiers. And then I will post the homework on Wednesday instead of Thursday. Although the next example, this example plus one more example going to be introduced on Thursday. In your homework two, there will be three problems, I believe, except for problem one. Problem two and three, you can already make it because one is about KNN, the other is about logistic regression. Problem number one gonna be something which I'm gonna introduce here, which is gonna be the comparison of different classifier. You can leave it till Thursday. Again, I would highly recommend everybody start homework ASAP. Absolutely don't delay it till the last day. Okay, let's finish our class today here, and I will see you on Thursday. And no worry, once the homework is posted, it probably will be tomorrow morning, or if I can make it fast enough, I can make it tonight. I will write everybody an email, and I will show the instructions, in the email, and on the first page of the homework. Okay. Have a good night. Thank you. Bye bye.